Hello everyone, my name is Yaroslav Golubev and I would like to tell you about our work on multi-threshold token-based code clone detection conducted at JetBrains Research and St. Petersburg State University. Let's start with the motivation. Research has shown that a significant part of the modern software code consists of duplicates, called code clones. It is important to be able to detect them, because research also shows that knowing about code clones within a project can help with its maintenance, and detecting code clones in large corpora of projects can be used for large-scale studies of coding practices. There are many different types of code clone detection tools, which use different approaches: tokens, syntax trees, metrics, and others. Despite being on the simpler end of the spectrum, token-based tools, and specifically bag of tokens-based tools within them, are still widely used because of their good scalability. However, research has shown that a lot of problems in clone detection arise because of difficulties with choosing specific parameters for such configuration. Therefore, we propose to detect more diverse code clones by running clone detection tools with several parameter configuration and merging the results together. A lot of research exists in this area. On this slide, we list some key ones. Notably, Wang and colleagues studied papers about software cloning and discovered that of those that mention empirical evaluation, 61% mentioned problems with choosing parameters. To overcome this, the authors present a tool called EvaClone that searches for optimal configurations by considering agreement between several clone detection tools. To describe our approach, let us start by describing the concept of a possible clone space. From the standpoint of bag of tokens clone detection, any pair of two code fragments, not only clones, can be described using two numbers: their length in tokens, the length of the smaller one if they are different, and their similarity, the number of common tokens divided by the number of tokens in the larger fragment. These two numbers can be used as coordinates on a plane, and all pairs of code fragments can be found on this plane. For example, in this case, pair A contains code fragments that are larger and more similar than those in pair B. When a researcher chooses parameters for bag of tokens clone detection, they choose a similarity threshold and a lower token length threshold, so that only fragment pairs that are larger and more similar than the thresholds are considered to be clones. However, it is reasonable to assume that valid code clones are not spread evenly across this plane. Naturally, more of them lean towards the right, where there is a higher similarity. By choosing one configuration, researchers may lose many additional clones. We propose to detect code clones using a parametric curve, similarly to how it is presented in the slide. The idea stems from the following observation. Larger code fragments have more room for modification that would still leave them similar enough to be considered code clones. Therefore, it is possible to detect clones in a corpus with different parameter configurations and then merge the results together. The main problem with this idea is the significant amount of extra time and computations necessary. In this example, fragment pair A is discovered in 3 separate searches. Ideally, we would prefer to detect all code clones with no overlap at all. Let's say we have 2 of the following arbitrary configurations adjacent on the parametric curve, and we want to find the upper limit for the 75% similarity search. Clone detectors can set not only lower token length threshold but also upper token length threshold, so it seems like we can simply set 60 as the upper limit, right? Unfortunately, no. Such limit would leave out some borderline cases. Say we have a code fragment of 65 tokens and a code fragment of 55 tokens, and let's say they have 49 tokens in common. This means that their similarity is 49 divided by 65, which is 75.4%. This means that such a code pair would be detected with parameters 75% and 40 minimal tokens, but with a hard upper limit of 60 tokens, it will be lost. This pair will not fall into any of the searches because one of the fragments will always be filtered out, so some overlap is always necessary. Still, it is possible to find an upper limit, it just needs to account for the most extreme cases. The largest block that will not be considered by the next search, with a lower threshold of 60 tokens, is, naturally, 59 tokens. All fragment pairs where both fragments are larger than 59 will be detected by the next search. The largest block that can form clones with it at 75% must contain all of its tokens. We can calculate that it will be 78 tokens. Pairs of 59 and 79 tokens do not need to be considered because they cannot be clones at the similarity threshold of 75%, and pairs of 60 and 79 tokens do not need to be considered because they will be found in the next search if they're clones. Therefore, we can put an upper limit of 78 tokens for the search and lose nothing. In general, all the upper token length thresholds can be calculated similarly using this formula that contains a lower token length threshold of the next less similar search and a similarity threshold of a given search. Finally, let's move on to our methodology. Let us describe how we obtain the parameter configuration. In our work, we evaluate the proposed approach for two prominent bag of tokens-based clone detection tools, SorcererSC and CloneWorks. The parameter configurations were obtained by the first two authors by manually labeling clone pairs that were discovered in a dataset of 3 projects, Spring, Guava, and OpenGDK. With each tool separately, we conducted 31 runs, from 80% down to 50% similarity with a step of 1%. The majority of papers used similarity thresholds in this range. We then took all detected clone pairs at the most similar search, 80%, and started picking samples from largest to smallest, labeling them as either true positives or false positives. We stopped when the precision was equal to 90%, which we considered to be acceptable, and the size of the last fragment was chosen as a lower token threshold. On the next step, we took the results of the next search at 79% and repeated the process. When all the searches were labeled, we drew the token length thresholds in a single table, and if adjacent similarity threshold had the same lower token length threshold, we only left the least similar ones, as visualized in this figure. Finally, we calculated the upper token length thresholds. In this slide, we can see that the resulting parametric curves for the tools look similar to one another. Also, the least similar search has no upper limit because it has no next search, but this should not present a problem because there are not many code fragments this large. Let us now discuss the evaluation. We evaluated the approach on 3 datasets. First of all, we compiled a small dataset of 3 projects that altogether consist of only about 45,000 blocks. Secondly, we also selected IntelliJ IDEA because it is an order of magnitude larger and because code clones within a single repository can be different than between unconnected repositories. Finally, we used BigCloneBench to compare the recall of CloneWorks with and without the parametric curve. These are the results of the first 2 datasets. On the left side, we can see the comparison of the amount of detected clones. It can be seen that both tools discover more code clones in both of the datasets. On the right side, we can see the comparison of the operation time. SorcererSC has a relatively long clone detection stage, and therefore the optimization can cut the time by 12% for a larger dataset, because fewer fragment pairs need to be compared. CloneWorks has a relatively short clone detection stage, and therefore running the tool 8 times is not significantly longer than running it 1 time, because in both cases, tokenization stage needs to be conducted only once. In general, it can be expected that for even larger datasets, our approach will be even more efficient. As for the BigCloneBench results, it can be seen that implementing the parametric curve significantly increases the recall of strongly type 3 clones, while also increasing the recall of type 2 and very strongly type 3 clones a bit. Let us quickly list the threats to the validity of our study. First of all, the approach is only targeted at bag of token-based clone detectors. However, such tools are very widely used. Secondly, we limit ourselves to Java, to 2 specific tools, and to specific projects for evaluation. Finally, we used manual labeling because of a large number of tested configurations, and only 2 authors estimated the parameters. It is desirable to conduct a more thorough evaluation of the precision of the parametric curve. Let us conclude now. First of all, we propose an approach to detect more diverse clone pairs for bag of tokens-based clone detectors by running the tool with different parameters and merging the results. We also propose a possible optimization for this approach. We estimate the necessary parameters for 2 popular tools, SorcererSC and CloneWorks, and finally, we evaluate the approach on 2 different datasets of various sizes and study its recall on BigCloneBench. We believe that this work can be continued in different directions. It is interesting to consider different ways to obtain the necessary parameter configurations automatically, for example, by using the EvaClone tool. It is possible to test the same idea for different code representations, for example, by comparing subtree sizes in the approaches based on syntax trees. Finally, it may be of interest to study code clones and the practices of code cloning from the standpoint of the possible clone space. Thank you very much for your attention. On this slide, you can find QR links to the paper and additional materials, as well as our license violation study that uses the proposed approach. If you have any questions, feel free to contact me at this address. Thank you.